The ideal gas law. Today's goal is we're going to learn about the ideal gas law, which we will deem as the snapshot law when we take a look at a gas at a moment in time. The ideal gas law states that it's a theoretical gas composed of a set of randomly moving point particles that interact only through elastic collisions. The law is derived from the fact that the ideal state of any gas, given number of particles, occupy the same volume, and that volume changes are inverse to pressure changes and linear to temperature changes. We're going to look at ideal gas law and how it behaves at STP. So recall that STP is called standard temperature and pressure, where the standard temperature is 0 degrees Celsius or 273 Kelvin, or 1 atmosphere in pressure. The ideal gas law combines all the gas laws together, and it can be derived either experimentally or theoretically, and the equation is PV equals nRT. The ideal gas law holds true for all gases and mixtures of gas as long as they are ideal gases. So P equals pressure, which can be in any unit. V stands for volume, has to be in liters. N is number of moles. T is temperature, and it has to be in Kelvin. And R is what we call the gas law constant. R we use as a gas law constant, and we can use two numbers, either 0.821 or 8.31. We use those accordingly based on either if we have pressure units in atmospheres, we're going to use 0.821, or 8.31 when we have kilopascals. Take a look at this problem. What is the volume of 1 mole of helium at STP? Well, when we plug it into PV equals nRT, we get N times R times T divided by P equals V. Plug in our values, and we get 22.4 liters. Now remember this value because this is a constant. Any gas at STP, 1 mole has the same volume of 22.4 liters. The ideal gas law equation and molecular mass. So PV equals nRT, where N is the number of moles, and N is equal to the mass divided by the molar mass. When we plug this in, when we plug in G divided by MW, we get PV equals G times R times T divided by MW. We can use this equation when we don't have moles. So it says, here's a sample problem. It says calculate the molecular weight of a compound of 0.109 grams occupying 112 milliliters at 100 degrees Celsius and 750 torr. When we plug in our values, we're going to solve for MW, okay? And when we do that, when we rearrange our variables, G times R times T divided by PV equals MW. When we plug this in, remember that our degrees Celsius has to be in Kelvin, our 750 torr has to be in atmospheres, and our 112 milliliters has to be in liters. Plug those values in, we get 30.2 grams per mole for our gas. Gas density, remember, is the mass divided by the volume. A low density gas has a bigger volume compared to its mass, and a high density gas has a bigger mass compared to its volume. When we rearrange our variables, we get P times MW divided by R times T, which is equivalent to the density of a gas. So here's a sample problem. What is the density of NO2? What is the density of NO2 if it occupies 1 liter at 1.24 atmospheres in 50 degrees Celsius? Again, you got to change the degrees Celsius to Kelvin, and we need to figure out our molar mass of NO2. So when we do that, we figure out that the molar mass of NO2 is equivalent to 46 grams per mole, and our temperature is equivalent to 323 Kelvin. We have those two variables. We're going to plug it into our equation to find its density. And when we do that, we get those numbers. Notice how all the variables cancel out except grams divided by liters, and we get 2.15 grams per liter.